All right, good morning, everybody. So today we're going to be covering note 7.1, the Pythagorean theorem. But before we can talk about the Pythagorean theorem, we actually need to talk about something that you did in the past in middle school, which was simplifying radicals. So the first thing we're going to do, just like it says on the paper, we're going to list all perfect squares between 0 and 100. We actually are going to take it a little bit higher up there. And we're going to talk about their square roots. Now, when something is a perfect square, technically it means we're asking that something has a power of 2. A power of 2 just means that 1 times 1, right, multiplied to itself is just a 1. And then if you notice, when we take a square root, we get that 1 back. So a square root is technically the inverse of a power of 2, the way we see it here. If we say 2 squared, well, that would mean 2 times 2, which is, of course, a 4. And when you take a square root of a perfect square, notice how we get that whole number back. It was the 2 that was multiplied to itself to give us that value of 4. So these numbers here are what we call the perfect squares. Now, we don't have them written on this side yet. We will, of course. But these are the perfect squares we're going to be working with in our assignment. And knowing these 12 will just make your life easier when you get into those higher level math classes. So when we say 3 squared, yes, there's 3 times 3. There's my 9, and the square root of 9 is 3. But let's finally do some that are kind of on our own. So when we say 4 squared, 4 times 4, that's 16. So again, what that means is if I take a square root of 16, which is a perfect square, I should get a nice whole number, which in this case is the 4. And when you take a square root, remember that number comes outside of this radical symbol, and we're left with just the 4, not the square, not the double 4 here that we wrote, just the 4. So that's why 5 times 5 is 25. So the square root of 25 is that single 5, the whole number that we would get for it. The 6 times 6 is 36. So the square root of 36 would be a simple little 6. So again, there's a connection between a perfect square and a square root. They are inverses of each other. We can think of it as a square root will cancel out a power of 2, and vice versa. Power of 2 can be canceled with a square root. So 7 times 7, yes, that's 7 squared. That would be 49. And so obviously, if I take a square root of that same 49, my answer would just be a 7. And the process just continues. And again, it's a good idea to know these values up to your 12s at least, right? Until your multiples of 12 here. So here we take a square root of 64. So of course, it's the 8 that was given a power of 2 to get that 64. 9 times 9 is 81. So the square root of 81 is 9 by itself, just a single 9. 10 times 10 is 100. So the square root of 100 is just that single 10. Here's a 121 for 11 times 11, or 11 squared. And 121, the square root of 121 would just be the single 11. And finally, the 12 times 12 is 144, aka 12 squared. But when I bring in a 144 in here, the square root of that is that 12 coming back out. And so when you have these values here, right, all these perfect squares written out, if you start to see them directly in a problem like this one where it says a square root of 25 and you go, hey, that's from my list. If it's from our list, then we don't waste time. No hesitation. My answer is 5, and that's it. There's my answer because I know it's going to be a nice whole number. I don't need to do any extra work for it. We just give the solution right away. Now, the square root of 18, on the other hand, 18 is not on this list. And when the number isn't on the list, well, that just means we're going to break down that number. We call it the tree method. It's what we learned back in our middle school days. So when it's an 18, we have that's 2 times 9. Now, the 2, the only thing that multiplies to give me a 2 is 2 and 1. So that officially makes it a leaf of my tree. Now, the number 9 can also be written as 3 times 3. But now the 3, nothing can reduce that. It's a prime number. So the only thing that multiplies to give you 3 is 3 times 1. So we circle it and we say it's a leaf of the tree. And then the idea is now we write every single leaf of our tree inside of a square root. And remember what we just saw. When we were talking, I'm going to bring up the 3 because I see it here. I see a double 3. Well, look, when you have a double 3, yes, that became a 9. But the idea is for every matching pair, remember, it has to match a pair here. It has to be 2 of that same number. One of them is going to come out of the box, just like here. There was a 9. Well, that was 2 3s involved. only one of the threes comes out. Now that 2 that was left in there, that didn't have a matching pair, so then we leave it inside. Can be strange. Let's try this again. 125. Let's see. Nope, it's not on my list. So then I break it down. And remember, you break it down into any numbers you can think of. This thing ends in a 5, so I know 5 will go into it. I can use a calculator now so we can figure out, well, what's 125 divided by 5? And so I get 25. Now, the number 5 is a prime number. Only 5 times 1 will work. But the 25, I can break that down even more into 5 times 5. So you keep breaking down the number as much as you can. And then when you get something like, oh, 5 times 1, then you circle it. It became a prime number. So I have 3 5s here. All right, well, remember what the rule is. When you're simplifying radicals, the rule was for every matching pair, only one of those numbers comes out. Now, this one here didn't have a matching pair. And if it doesn't have a matching pair, then we leave it inside the radical symbol, in this case, a square root. And that would be my answer. So again, when the numbers do not come from the list, we start to break them down into prime factorization. When the number's from the list, we'll give the answer right away. You don't need to do this tree method, right? Prime factorization with the number that's a perfect square already. So the number 42, let's see, it's not on the list. Then I'm going to do my prime factorization, and anything that multiplies to give you a 42, go with it. So for instance, 7 times 6. Well, 7 times 6 is 42. 7 is already a prime number. All right, so we can go with that. And of course, we continue to break down the 6. So there's a 2 times a 3. So a 2 is a leaf, a 3 is a leaf, because the only thing that multiplied to give me a 2 is 2 times 1, a 3 times 1. So we know they're all leaves. So that's it. I have no more branches. So I'm going to put all of this in here. 2 times 3 times 7. And now it's time to start looking for a matching pair, but there is no matching pair. If there's no matching pair, then that just means one thing. I get to multiply all these numbers back, which I already know what it was. It was radical 42. This is my answer. When you don't have anything to bring outside the radical symbol, then you just leave it alone. And then it's okay to leave our answers like that. All right, 80. Oh, got close, but it wasn't on the list. So here we go. Let's see. What gives me an 80? Well, that's 10 times 8. That's an 80. And again, it could be any two numbers you want. Well, a 10 is 2 times 5, and nothing divides a 2 anymore besides 2 and 1. A 5 is just 5 and 1. All right, let's continue with the 8. Well, that's a 2 times a 4, but a 4 we could keep going. 2 and 2. Remember, you break down the numbers as much as you can. Just remember, when you're writing this out, I have 1, 2, 3, 4, 5 leaves. I better have 5 numbers in here. And there's 4 of these here. And a single 5. Notice how everything's still multiplying on the inside. All right, but here we go. We have a matching pair. Then a 2 comes out, just 1. We have another matching pair. Well, now another 2 comes out. And no, it's not a 22. Remember, they were multiplying. They continue to multiply even though they're out on the outside now. And then the 5 didn't have a matching pair. So we leave that inside the box. That was the idea. If it doesn't have a matching pair, we leave it inside. And so 2 times 2, yes, we multiply that back, and we get 4 square root of 5 as our answer. And finally, again, this is just review. The square root of 200, again, 200, all right, it's too big for our list here. But we know that 200 is 2 times, well, 100. The 2 is already a leaf. Now, there is a little shortcut that you can find here. For instance, what gives me 100? Well, 10 times 10. Well, if you notice, they already have a matching pair. Technically, it's not a prime factorization, but because they're a matching pair, I can actually stop already. And I'll bring these numbers in. Look, I have a 2, a 10, and a 10. Again, when you see a matching pair happen like this, then just stop the prime factorization. Here's the matching pair. So the number 10 comes out. That one didn't have a matching pair, the number 2. Then we leave it inside the box. And just like that, we saved ourselves a little bit of time there. because we saw a matching pair happen instantly. So that finally brings us to today's concept, which is a Pythagorean theorem, which is also back from your middle school days. And before we talk about the Pythagorean theorem, well, we have to know what a right triangle is and what a right triangle looks like. And so there's special names for every side of a right triangle. And that's what we're going to work on right now. So a right triangle, first of all, has to have a right angle in it. And here we have our three sides. But there's something called the hypotenuse. Now, the hypotenuse is basically the longest side. The longest side of a right triangle. I'm just going to use the symbol for right triangle right there. So it's the longest side of a right triangle. And when I look at this picture, you should notice something about the hypotenuse. This is the one right here that looks like it is the longest side in this triangle. So that right there is what we would call the hypotenuse. So from K to M. So this line segment, K to M, would be the hypotenuse. I'm going to put height for short. But what I want you to notice is this. When I'm looking at that side, look how it's right across from the 90. So the 90's here. The hypotenuse has no contact with the 90. So we also like to say that it is across from the 90-degree angle. So again, that's why we bring in our symbols here. And then the only other word that we see here is obviously it says the legs. Now it's plural because there's more than one, of course. But when you're talking about the legs of a right triangle, these are the sides. If I can get a pen that works there. But yes, these are basically the sides that make the 90-degree angle. And so when I'm looking here, well, again, they're very easy to spot there. These are the two sides here that actually touch, right, or create the 90-degree angle. So then those are the legs from K to I and I to M. So it's going to be very important to spot these because this is what's going to help me set up my Pythagorean theorem. So again, here we have our sides, or the legs here. So let me put it in this color over here. So the legs, plural, because yes, we have two of them there. Now, when we're setting up the Pythagorean theorem, it says in a right triangle, if A and B are the legs, okay, well, look, here's the 90. That means these are the legs. C is the hypotenuse. Okay, there's the C. So I'm just putting the letters where they belong, right? The letter C is the height, they said. So that's why we're writing that over here, right across from the 90. So we have to recognize it. And then here comes the Pythagorean theorem, which says A squared plus B squared is equal to C squared. The only thing to remember here about the Pythagorean theorem is this. These are the legs. The ones with the plus sign are the ones that are considered the legs. Those are the sides that'll go there. And then the C is the hypotenuse. The hypotenuse should be the one that's all by itself. Very important, though, to note is that they all have to carry a power 2 when you start the process of Pythagorean theorem. Everything should have a power of 2. So let's start with an example here, of course. So as we start with the example, well, we're looking at this problem very carefully here. Give it a little brighter light there. Okay, so it says solve for x. Do the side lengths form a Pythagorean triple? Okay, so there's something else that we have to talk about here. So first of all, we're just going to solve for x. When I look at this, I'm going to look for my height first. So there's the hypotenuse. Once I spot it, I know this is the number that should be by itself. So it says a squared plus b squared is equal to c squared. So everything should carry a power of 2, just like we're doing right now. Notice I'm not worried about values. The hypotenuse is the 10, then that's the one that's going to be all on its own. And then, of course, now we know that the legs, the ones that actually touch the 90 are the 6 and the x, so it doesn't matter which one you put first. The calculation will be the same no matter what. So x squared, well, that's just x squared. 6 times 6, remember that's why we have that list up on the top, is actually 36. And then, of course, 10 squared is 100, just like we see at the top of this page. Now we're solving like we do any other problem in algebra. We will subtract the 36 from both sides. And so it says x squared is equal to 64. And now here comes the big thing that we were talking about earlier. In math, there's only one thing that will cancel out a power of 2. And the only thing that cancels out a power of 2 in math is, well, a square root. Remember, a square root and a power of 2 are kind of opposites. They're inverses of each other. So I am going to give both sides a square root, because once again, that cancels the power of 2 and the radical. They cancel each other out. They're inverses. So x is equal to, and now when I look at this number, it is at the top of my list on the top of this page. So I know my answer is a nice little whole number of an 8. And so to answer their last little question, they said, do these form a Pythagorean triple? Well, let's look at the list of numbers. When I'm looking at the list of numbers, look at the sides. The sides are 6, 8, and 10. Look at how they're all whole numbers down there. 6, 8, and 10. They're all whole numbers, no decimals, no radicals. Then the answer is yes, they are Pythagorean triple. Again, a Pythagorean triple just means that they followed the Pythagorean theorem and everything was a nice whole number. So when I look at number 3, it says solve for x, simplify the radical, do the side lengths form a Pythagorean triple. Okay, and we're going to get that question on the assignment as well. But when I look at this one, here's the 90. That makes this the hypotenuse right here. All right, here we go. I'm ready. I'm going to go right into it this time. Something to the power 2 plus something to the power 2 equals something to the power 2. Remember, everything should start with that. But the height this time, the hypotenuse is the x. Look at where the x is this time. Notice the x isn't always going to be in the same spot. It just depends what's given to us. So these are the legs 4 and 6. So as I'm working with 4 and 6, here we go. This is 16. This is 36 is equal to x squared. I'm going to add these two. I don't need to subtract. This is straight addition. So then I get 16 plus 36 is 52 is equal to x squared. And of course, just like we said earlier, the only thing in math that gets rid of a power 2 is a square root. So I'm going to give both sides a square root. Now, we kind of need to check this because 52 is not on my list. But now I need to double check and see if I can actually reduce this. And we could do that off to the side somewhere. So for instance, I could take that 52 and start breaking it down with some prime factorization. For instance, 2 times 26 is 52. And yes, that's a prime right there. The 26 is 2 times 13. All right, we have a leaf. And then the only thing that gives me a 13 is 13 times 1. So we have a leaf there. So notice how this radical is now 2 times 13. And yes, I do see a matching pair. And we said for every matching pair, one of those numbers will come out. And there's my answer for x. But now to answer that last little question that they threw at us earlier, they said, will this be a Pythagorean triple? Well, notice, look at my sides. My sides are 4, nice whole number. 6, all right, looking good. It's a whole number. And then 2 square root of 13. That is not a whole number. That radical 13 means that there's a decimal that we would have gotten if we used the calculator for a problem like this. So because we see a radical or a square root, if we see a decimal, then that just means this is not a Pythagorean triple. So we're just going to try to cut it short there. Okay? Now, they're going to change the question up. Pythagorean theorem can be used for a couple things. So one of the other things that we can use the Pythagorean theorem is for problems like number 4 and number 5, where they're asking, all right, I have a triangle that has a 5, a 7, and an 8 as the sides. The question is, do they truly form a right triangle? Well, remember what Pythagorean theorem says. It only works for right triangles. So that means a squared plus b squared has to equal c squared. But in this one, this kind of question, we are questioning that equality. So let's set it up here. Everything has a power of 2. There's the c. Well, actually, let's put a parentheses there. The question is, will they equal each other? Now, remember, the one that goes out here on its own is the hypotenuse. Well, the biggest number, right? The biggest side, there's your hype. So then we're going to put an 8 in here. So the 5 and the 7 go over here. So we're just plugging numbers in. You have to understand, we're not even solving anything. So it says this is 25. This one is 49. And the question remains, will it equal? Well, 8 times 8 is 64. Well, all I'm doing is adding. Remember, I'm not solving. I'm not going to move anything. I'm just literally combining like terms. So 25 plus 49 is 74. And no, 74 does not equal 64. That is a false statement. And if this is a false statement, well, then this is where we can write out our note for something like this, where we basically say, no, this is not a right triangle. So the sides 5, 7, 8 do not form a right triangle. Now, they probably do form some sort of triangle. It's just not a right triangle. And that's what the question was asking. So there's our answer. Our answer is our little statement where we say, yeah, this is not a right triangle. Well, let's try one more. It's asking, okay, is this a right triangle? This is the biggest number I see. So this is the hypotenuse. All right, so now I'm ready. Something squared plus something squared should equal something squared again. And again, the height, which is the 13, should be by itself. That means these are the legs. So the 5 and the 12, again, the order doesn't matter. 12 or 5, 5 and 12. So 25 plus 144. This is me giving everything a power of 2. You can use a calculator if you need it. 13 squared. Well, that's 13 times 13, 169. The question is, though, will they be equal to each other? Well, just do the basic math. 25 plus 144, that's 169. And yeah, look at that. We finally have a perfect match. It checks out. So what does that mean for us? It just means the sides 5, 12, and 13 do form a right triangle, which again, that's what the question is asking. Will they create a it's not just will they create a triangle. No, they're being specific. They're saying, will it be a right triangle? And for our last question of the day, it's a little bit of a word problem, but if you read it, you'll understand that it's actually just Pythagorean theorem again. It says there are 2 paths that one can choose to go from Sarah's house to James' house. One way is to take C Street, all right, so a straight shot there. The other way requires to take A Street, this street right here, and B Street. So how much shorter is the direct path to along C Street? All right, well, there's 2 paths, right? There's the direct, and then there's the long way around, A and B Street. Well, let's find that one. That one's actually shorter. So the long way, which is the A, B Street here, well, all I have to do to figure out that distance is add 2 plus 1.5. So that's a total distance of 3.5 miles. All right. So that's if we go the long way, right? That means we went this way, made a turn, and then ended up at James' house. So this was the long way. All right, but notice this is a right triangle. So because this is a right triangle, then we're going to look for the short way, right? What's the fastest way there? Well, from here to here. This is what we're looking for. This is the short way. And in reality, we're just going to call it x for now. So here comes Pythagorean theorem. And yes, there's a decimal. That means my answer will be a decimal as well. So be careful with that on the classwork. Something squared plus something squared equals something squared. And yes, of course, this one is the hypotenuse. So this is the one that should be by itself. And so here we have our 2, we have our 1.5. We start taking care of the calculation. 2 times 2 is 4. 1.5 squared, though, just double check that with a calculator if you need to. But 1.5 squared is 2.25. And that's equal to x squared. All right, well, I'm just going to combine these two. So that's 6.25 is equal to x squared. And now, as usual, here comes that square root. That's what cancels out that power of 2 here. That's why the x is just kind of on its own. And now we're just going to use a calculator. 6.25. I'm going to take a square root again. Feel free to use Desmos there. And I get 2.5. What was this in miles? So the short way is 2.5 miles. The long way was 3.5 miles. But notice the question they said, how much shorter is the direct path along C Street? So they're not asking for this answer right here. They're saying, how much shorter is this compared to this number? So taking the direct path would be, and then look, this is where you have to do the calculation. You go 3.5 and you just subtract 2.5. And notice how that's just, you would be 1 mile. Taking the direct path would be 1 mile shorter. So yeah, we used Pythagorean to find that distance, but if you read the question carefully, they actually wanted me to subtract. So look out for that when you do the classwork. All right, with that said, have a wonderful day. We do have a test coming up. We have pushed it because of these meetings that I'm in. We are pushing it to next week, which is why we started this unit just a little early. With that said, have a wonderful day, and I will see you later this week.